So good day, everyone. There are many fundamental logical equivalences that we often encounter. Suppose we have statements P, Q, and R, then the following logical equivalences hold. First is the domination law. So the first domination law states that if we take the disjunction of P or T, then it's logically equivalent to a true value. Okay, well, let us look at the truth table. Suppose we have P, so it has values true or false, right? So, and we take its disjunction with a true value, okay? So P or 3, T. So this will result to both true, okay? We have already established that if we use OR operator, or this is the disjunction, so it will evaluate to true if there is at least one true. So given that there is already a true value in here, then it's only logical that it will evaluate true or will be logically equivalent to true. Now, the another domination law is that if we take the conjunction of P with a false value, then it is logically equivalent to false. Okay, so let us look at the truth table. So we have P, either true, false, and paired with false. Okay, and if we take the conjunction P and F, so this will result to both false. And we have already established that if we take the conjunction of or and of a statement with a false, then it will result to false. It will only be true if both are true, right? So this will result to false. Okay. Now the identity law is that taking the or the and of P with a false or true will evaluate to itself. Okay. So we have, say, P, and we're writing the truth table, and we have the false. Okay, we take the disjunction of the or the or of P or F. Now, this will be true if there is at least one true. So the other one is false. And we can see that the truth values of P, which are both true and false, is similar to the truth values of P or false, which also results to true or false. Okay, so we can say that this identity law is valid and correct. Now, another identity law states that P and true is logically equivalent to P. Okay, so we have rewriting P again. We have true, false, and true. So taking the conjunction of P and true, we're taking the and, so this will result to true or false. This is false because of the presence of false in here. Okay, and we can see that the truth values of P, true and false, is similar to the truth values of P and P. So we can say that this identity law is valid and correct. Now we have the double negation law. The double negation law states that if we take the negation of a certain statement, then it will evaluate to itself. Okay, so we have the P and taking its negation, and we will take the negation of the negation again. So we are basically sandwiching this inside another negation operator. So let us see the truth table. So P could either be true or false. So its negation, true will become false, false, true. Now taking its negation again, so false becomes true, and true is now false. This is true, I mean, and true becomes false. Now we can see that this column, in this column, have equivalent truth values. So we can say that they are logically equivalent. Okay. Now the absorption laws, it says that the P or the group na P and Q is equivalent to P. Okay? And the other absorption law states that P and P or Q evaluates to P. Okay? So we can verify that using a truth table. So we have the P and Q. So since we have two variables, this will evaluate to 4 truth values. So we have true, 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 false, false, true, and false, false. Okay, now taking the for the first one, the P and Q. So this will only be true given two true values. So the rest will be false. Okay, now let us take the P or the P and Q. Okay, so this will essentially evaluate to taking the OR of these two in a columns. So we will have true, true, false, in false. So we can see that the column P, the column of P or P and Q have the same truth values and therefore logically equivalent. Okay, so that will be the same for P and P or Q. Okay, so this is also expected to have truth values true, true, false, false. Now, let's move on to idempotent laws. So the idempotent law states that if you take the and or of a certain statement with itself, then it will evaluate to itself. Okay, so basically we have P, say, and it could be true or false. And let's just duplicate P, which is also true or false. Okay, and if we take its conjunction, P and P, so we take T and T, this will be true and also false since both are false. But the P or Q will also evaluate to what? So true or true, true, false or false, also false. And you can see that these two columns, P and P, this should be P or P are logically equivalent to P. Okay. Now we also have the commutative laws. The commutative law states that the P and Q is logically equivalent to Q and P. Similarly, the P or Q is logically equivalent to Q or P. So what happens here is we are basically just switching the position of P and Q. Okay. Now for the associative na laws, so it states that the group na P and Q and R is logically equivalent to P and the group Q and R. So similarly, P or Q or R is logically equivalent to P or Q or R. So basically what it means is, suppose we have P, Q, and R, and they are connected by similar na operator like the and the or. Okay, so this and or na statement are left or right na associative. In other words, it is okay if we group it as P and Q and R, or group it as P and group Q and R. So that will be true also for the or na operator. But it is not true if, let's say, we have P implies Q implies R, and we have, let's say, we have P implies Q implies R, and P implies Q implies R. This left or right na associativity will not be true for the implication. So these associative na laws are true for the for the and the or na operator. Okay. Now we have the distributive laws. So we are basically distributing this P to the group Q and R. So you can think of it like you have the A and B plus C, and you will distribute A to both sides of B and C. So this will result to AB plus AC. Okay, so that will be true for the distributive na laws. Suppose we have this P and Q, P or the group Q and R. So taking this P or, so we will distribute it to both sides of Q and R. So giving us P or Q and P or R. And we will simply copy this and the operator that is connecting Q and R to this. Okay, now we also have P and the group Q or R. So this is logically equivalent to P and Q or P and R. So the same concept with the first na distributive law, this P and it will be distributed to the two factors Q and R, which will give us P and Q, P and R. And the connective that is connecting Q and R will be simply copied. Okay, now for the De Morgan's na law, we are taking the negation of P or Q and the negation of P and Q. So note that the and or the not na operator is being applied to the whole na group and not just to P. Okay, take note of the parenthesis. Okay, now if we take the not na operator or negation of this whole na expression that is being connected by and, so what will be the result? So basically this not na operator will be distributed to the P and Q, negating both sides, which will give us not P and not PQ. And note that this or na operator is replaced with and. Okay, so again, the not na operator, you distribute that to both P and Q, negating P and Q, and the or will become and. Now, the taking the negation of P and Q. So this negation operator will be distributed to P and Q, negating P and Q, resulting to not P and not Q. And this and the operator is replaced with or. Okay, now we have the negation laws. So the negation laws that states that the first one states that P or not P. So in other words, we are taking the disjunction of a certain statement with its negation. It will reevaluate to, or it is logically equivalent to true. Okay, suppose we have P or, sorry, we have P and not P, and we have another column P and or not P. Okay, so we have true, false, false, true. So taking the or of this, true or false, true, true. So you can see that the results are all true. So we can say that this negation law, P or not P, is a tautology. Okay, now we have the P and not P, or taking the conjunction of P with its negation, it will evaluate to false, or it is logically equivalent to false. So we have P, not P, and we have P and not P. So we have true, false, false, true, and taking the negation, this will result to false because of the presence of the two na false na values. So we can say that the P and not P is a contradiction. Okay, now we will be having some examples.